All right, let's get started. Welcome to the session on designing functional programs. My name is Venkat Subramaniam. We're going to talk about how do we approach some of the concerns we normally have when it comes to designing functional applications. Just to quickly set the stage where this kind of talk came from, I've been giving talks on programming with functional style in Java for quite a number of years now. And almost always, when I finished my talk, I would have people come up to me and ask some questions. And there was a very common theme of questions that happened almost every single time I gave a talk. It's like, oh, I've heard this question so many times. And so I said, well, that really means it deserves a talk on its own. So I kind of grabbed some of those questions and created a talk out of it. So I really want to talk about how do we really approach designing some functional systems. Also, what are some of the deficiencies of the functional style of programming in Java, where it may fall a little flat, and where we may have to do a little bit different. This is not about functional programming in general. This is pretty much about how do we deal with this in Java, because the tools we use often constrain what we can do. While there are concepts and theories and practices out there, we may not be able to do all of that the way we want it to do, depending on what tool and environment and language and framework and libraries we use. So this is pretty much about the world that most of us in this room live in, which is, hey, we're programming in Java, we have adopted Java 8, we're programming in functional style, but how do we really approach it? That's kind of what I really want to focus on in this talk. So in terms of functional programming, so what is really functional programming? Well, we are trying to do function decomposition. That's what we're really trying to do. One of the things that really frustrates me when some people who are practicing functional programming go out and say, gosh, this is great, we don't have to do objects anymore. To me, that's trying to throw the baby with the bathwater, right? I don't have a problem with object-oriented programming. I have a problem with the way people use object-oriented programming. So the problem is not in OO, the problem is in how it is being used by a lot of people. And I strongly have benefited from object-oriented programming, so I don't want to throw it away. But in that regard, I want to look at it a little differently. So what am I really trying to do when I try to program in functional style? What am I really approaching? So if you really look back in about 20 years of Java programming, we all can agree that we've been programming in object-oriented systems, right? So we've been doing object-oriented programming. So that's kind of summarizes, that's what we've been doing. But let's be really honest about it. There's nobody who has ever written object-oriented code with only objects. It's impossible to do that. Because when you create objects, what is the next thing you do? You create methods and fields, maybe. And then when you create methods, what do? Well, how are the methods going to be implemented? Well, we got to write some code for implementing the methods. So what we've been really doing, honestly, is not object-oriented programming. We just keep saying it. What we've been doing really is imperative plus object-oriented, in all honesty, right? Because that's what we've been really doing. Imperative plus object-oriented programming is what we've been doing all these years. Because the methods we write and how we work with multiple objects, all of them have been imperative. And to me, there are parts of OO that really is bad. But there are parts of OO that is very powerful, very useful. And I don't want to let go of them. That's just my personal choice. My anger is not on object-oriented programming, right? But so the question is, what am I really trying to get to? Well, I'm going to still continue doing object-oriented programming, but I'm going to do it with functional decomposition plus object-oriented programming. So all I'm interested really here is replacing that part, not the right side. Because the right side is not my main problem. Sure, it can be done in a very poor way. I'm not saying that people don't do it in a poor way. But if I do OO in a really good way, then my problem is not to throw out OO. My problem is to throw out the imperative style, or at least replace it with a functional style. So in Java today, and other languages, for example, Ruby and Scala and Groovy, just Java is not the only language that does this. A lot of different languages, you can actually use object-oriented decomposition, but you can mix it with functional decomposition as well, and you can benefit from best of the both worlds. And that is one of the really rewarding things for us to do. So what I'm trying to do over the years is really get better at this part. Where can I apply object-oriented programming and where can I apply functional programming, and put them to really good use and benefit from each one of them because I find value in both of them. And of course, on occasion, I do have to admit, I do use imperative style of programming also. To me, these are just tools. I'm not biased towards one tool versus the other. I prefer functional style programming where it makes sense, where my life is easier, where I can actually benefit from it. But there are times when maybe an imperative style is better for the problem at hand, and I don't mind really using that in that particular context. So in that sense, what does really functional programming espouse? What does it really provide? Well, the very first thing we hear about functional programming, when you start reading about functional programming, when you start learning about it, what do they tell us? The first thing they tell you is, hey, you should not do any mutability, right? Assignmentless programming is extremely important. Don't do assignments. Don't change any variables and values. There are a good number of languages. I classify those languages as, so I classify languages into a couple of different ways within this context. I call them as purely functional programming languages. And then, of course, there are languages, what I call as a hybrid functional languages. Just like in object-oriented programming, you had fully object-oriented languages, but you also had hybrid object-oriented languages. One example of hybrid object-oriented language was C++, even though people will argue whether it's object-oriented or not. But I'm not really interested in that argument. It is a hybrid language as far as I'm concerned because I could do no objects at all in it, write pure C code in it if I want to, or I can mix and match it. Whereas if you take a very, very purely object-oriented language, it will not allow you to really have anything outside of objects. It'll enforce that, and objects are really becoming the paradigm. In that case, of course, you're still being imperative, but you're not entirely procedural on the outside. Much like this, there are certain languages which are purely functional programming languages. These languages will not allow you to mutate anything, period. There is no syntax for modifying a variable once you create it. You can spend hours and days together. There is no way you can change it. I teach a course on programming languages, and in that course I usually use about 8 languages, but my students are way better than me. Collectively we use about 20 to 25 languages in the course. It's a very rewarding course to teach because I come out learning a lot from this course. But in one semester, a student with about 15 years of experience came to me and said, I've used these languages, but I actually like a purely functional language better than a hybrid functional language, he said. I said, why do you say that? And the reasons he gave could be taken in 2 ways. And he said, the reason is, when I sit down to write code, I come from an imperative style of background, object style of background. When I sit down to write code, when a language is hybrid, I struggle with it for 15 minutes. I cannot figure out how to do it. I quietly go back to my old ways of doing things, and the language quietly lets me do it. On the other hand, this purely functional language beats me down, right? It takes me and beats me on my head and says, it's my way or the highway. And I cry, I complain, I curse, and 7 hours later, I'm still stuck, and then I go take a break, come back the next day, and finally things begin to work. And after all this frustration, I'm beginning to see the light of how to do this. So he said, from that point of view, I really like languages that beat me down and tell me this is the way to do it. I said that's exactly the reason why I also prefer hybrid languages. Because when I'm at work, my boss is going to beat me even harder, right, when I don't get the work done. So I'm really happy to say, you know what, this purity is all great, but I've got this in production. Now we can come back and refactor it. I'm a really pragmatic person rather than being a perfectionist. Yeah, I really want to do good things, but at the end of the day, I still have to continue releasing products as well. That's kind of the reason why I like these kinds of languages, because they do give you an escape route when you're stuck with something. So in that regard, there are some languages that don't have mutability at all available. So yes, surely we want to favor immutability, but that's one of the things that functional programming languages really espouse. The other thing is higher order functions. What in the world is higher order functions? Well, let's think about this for a minute. Again, in the context of Java and what we've been used to, what have we been doing so far? We may pass object to functions. I'm purposefully not using the word method. So just clearly to get it out of the way, to me a method is just a function. A method is a function that has association to a class or an object. So a function could be a freestanding function. A method is a function that's tied to a class or to an instance. So I'm just going to use the word function in general. We may pass object to a function. We may create after all, an object within a function. So sure, we can do that too. We are already doing that in languages like Java. And then finally, we may return object from function. I'm not trying to be grammatically correct here for good reasons. So this is what we've been doing. We're used to doing this. What is a higher order function after all? Higher order function is where we may pass a function to a function. We may create a function within a function. We may return a function from a function. So that's basically what makes a function a higher order function, is that we can compose functions using other functions to put things together. So we are using higher order functions to build stuff around it. So a higher order functions give us the ability, you can still take objects as parameters. You can still return objects as results. But in addition, you could also work with functions, receiving them, creating them, and returning them as well. So that gives us an ability to program with higher order functions where you are raising your bar. You're saying, I'm not only going to receive objects from you or data from you or primitives from you, I'm also willing to receive functions from you as well. That's basically what higher order functions give us. Well, this leads us to some really powerful things. And to me, while I'm really excited about immutability, while I'm really excited about higher order functions, to me, these are not the most important things to really work on. For example, if somebody comes to you and says, hey, what's really so cool about object-oriented programming? I'm not suggesting object-oriented programming is the one that introduced all of these, but what is really cool about object-oriented programming? Well, we could say that object-oriented programming is where we really honor abstraction, right? Sure, absolutely. And then we honor encapsulation. So absolutely, we want to really enforce encapsulation. And then, of course, we want to really have inheritance. And then, of course, what is the last thing? Polymorphism. But if you really think about it, among these four things, which is the most important thing? So polymorphism, which is the most important thing? Well, abstraction is not new to object-oriented programming at all. We've been doing abstraction for many, many, many centuries, even before we thought of programming, right? Plato introduced the concept of abstraction, if not being one of the first, certainly one of the first people to do this. We've been using abstraction every single thing we do. In every language we have ever written, we have abstraction in some form or the other. Maybe not all languages gave us the user-defined data types, but we can say that's great, we can have that. Well, so discard that. Encapsulation, well, sure, encapsulation is extremely important, but you could do encapsulation even within a function. Whatever local variable you put in a function is encapsulated, right? So this really extends and gives you other forms of encapsulation. That's absolutely useful. I'm not saying it's not useful, but I'm not going to just because I can do encapsulation. Sure, that's extremely welcoming. What about inheritance? The only thing we inherit is pain, because in this case, mostly this is really a cause of problem than a cause of strength. There's really a good variety of object-oriented languages that don't even care about inheritance. Unfortunately, when we program in one language predominantly, they blind us, and they sincerely do, unfortunately, because they really blind us. We're not able to think beyond it. This is one of the reasons I really want to learn different languages. That way, I will not think about anything in one particular way, right? So there's no one real way to think about things. There's so many variations. Inheritance is not really required in a lot of ways, and it's usually part of a problem than a solution most of the time. But that leaves us polymorphism. Though polymorphism is not unique to object-oriented programming, I really do object-oriented programming for polymorphic behaviors, because this is what gives me extensibility in my software. So to me, really, what is it we are really after? Polymorphism is to object-oriented programming. So this is what I'm really, really after when it comes to programming. Polymorphism is to object-oriented programming and what am I really going forward? So similarly, when it comes to functional programming, what do people normally tell us? Well, they tell us in the functional programming world, immutability is extremely important. This is like saying abstraction, encapsulation, all those good stuff. Similarly, they tell us that higher order functions are really important. Oh yeah, absolutely, I completely agree with that. Higher order functions are important. But the real charming feature of functional programming, in my opinion, really comes from two things. One is function composition, and the other is lazy evaluation. So these are the two most charming features of functional programming, and this is what I wake up every morning to enjoy when it comes to functional programming. These, to me, are the pathway to get me to this. I cannot do these without these two. But I'm not doing these two without getting these two, right? That's what I'm really after. So I'm going to say function composition and lazy evaluation is to functional programming, because that's what we really are after in terms of what our goals are to cherish as an important feature. Why? Because function composition gives us expressive code. We're able to really express the code as a series of transformations. It removes accidental complexity. The reason I'm not happy with imperative code is because of the complexity it brings in, the accidental complexity it brings into the code. Whereas the function composition removes that accidental complexity. It makes the code expressive, it makes the code easier to follow, it makes the code easier to understand, and that is one of the biggest gains I get out of it. But unfortunately though, I cannot just sell you that function composition is great and go home, because you're going to go try it and say, are you an idiot? Because this is going to create objects after objects after objects, and we're going to have really problem. The more garbage you create, the more garbage you have to collect. And we're not going to have good performance for large data set if we keep creating objects. But in all fairness, there's a lot of languages that do just exactly that. They give you the functional style, the function composition, but they do not give you the lazy evaluation. In those languages, when you create a large collection and go through a function pipeline, you will create a lot of intermediate collections along the way. But they don't seem to care about it for a couple of reasons, because most of the time people work with really small collections. It doesn't hurt performance. And again, pragmatically speaking, I don't want to complain about things that don't affect me. Hey, my collections are really small, the performance is reasonable, why bother? Be happy about it. But I'm personally working on large data projects these days. I deal with millions of data. Performance is the most important thing. Everything else comes after that. Having the laziness gives a way to really be efficient and expressive at the same time. That's one of the really biggest benefits we get out of it. So in other words, the immutability and the higher order functions are really nice, very useful, very critical. But what I'm really after is those two, function composition and the lazy evaluation. That's what I'm really, really after when it comes to these languages. What does this really help us? What does the purity help us with? And let's understand how this can be very useful. I love languages for what they do, because when languages know that a certain construct is very pure, there are optimizations languages can do. Let's take a look at an example of this real quickly. One such language is Haskell. Haskell is probably one of the languages that really amazes me, because I actually rejected the language a few times. I tried to learn it 3 times. I gave up every single time. And the 3rd time I sat down and said, you know, all my friends tell me it's a good thing. I trust them. I want to learn it. And here's what I had really hard time learning Haskell. Every single time I sat down to learn Haskell, I was trying to go through the static typing. And I'm not smart enough to even get it. And I just kept failing every time. And then one day I realized, oh my gosh, I've been doing this wrong. Haskell cares less about me telling what the type is. It's a language that has a very powerful type inference. It can figure out what the type is very smartly. And here I was trying to tell it every single detail, and I'm trying to really hurt myself. And nowadays, I don't put any type at all. Mostly when I write Haskell code, it doesn't seem to care, and we're really good friends now. And that's not the way we started out. So the beautiful thing about this is the language is actually very powerful in that regard. But I want you to think about one thing, defaults. And there are languages, this is purely a language fundamental, right? There are languages that do safe defaults. And then there are languages that do unsafe defaults. So I really spent a bit of time thinking about it. Look at languages like Haskell. It's safe defaults. Everything is pure. If you want to make something impure, you have to beg and say, please, this one time, please, only this afternoon, let me make this impure. And Haskell will say, not today. And it's like really, really, really hard to make things impure, right? You have to work extra hard to do it. In a language like Java, everything is unsafe mostly. You want to go to Java and say, could I please make this immutable this time? Please this time. And Java says, okay, I'll think about it. So it's a complete opposite spectrum of where things are, isn't it? And in that case, when a language can enforce purity, there are things it can do. I'll just give you one example of this where, just to share an excitement I have with this. Let's say I have an add function where add AB, this is a Haskell code, is A plus B. Well, sure, this is a very simple example, A plus B. But there is something that Haskell knows that languages like Java would never know. And that is, Haskell knows that this is a pure function. Because variables are immutable in Haskell by default. You cannot change them. And as a result, Haskell knows that this is a pure function. If you write the same code in Java, Java says, gosh, I don't know what you're doing in these functions. I can't guarantee purity at this point. A could change elsewhere, B could change elsewhere. I can guarantee that for you. Then I'm going to say over here, in this case, let's say I'm going to say, let's say evaluate value equals value. Again, a really stupid, silly example. Then I'm going to say main right here. And in the main is when I'm going to introduce some impurity. And this is basically saying, hey, I really want a sequential execution of this code. I got dependency on the ordering, stuff like that. So in this case, I'm going to go into a print. And then I'm going to say evaluate. And then I'm going to pass to it and add 1 and 3. Well, a very simple example, as you can see, but when I run this code, it produces a value of 4. But languages like Haskell can do something really different than other languages. In the case of Haskell, there are two distinctive evaluation models. One is called the normal order, and the other is called the applicative order. So, applicative order. And in this case, Java and most of the languages we are used to do what is called the applicative order. You know, it's really funny we called it normal order because it's pretty abnormal. Very few languages actually do this in reality. In a normal order, functions are evaluated not in the order in which you apply them. So if you were to look at this in your eyes of Java program, if I ask you when will add be called, you would tell me add is going to be called right away. Because add is going to be called right away, and the result of add is going to be sent to evaluate, and the result evaluate is going to be. Haskell says, never mind, I'm not going to call add. What are you going to do with add? Well, gosh, I'm going to send it to evaluate. What are you going to do with evaluate? I'm going to send it to print. Okay, that's a good reason to do it. It's absolutely lazy, right? And it postpones it, but it can postpone it because add 1 and 3 will never give you a different result in a million years. It's pure. And that's one of the properties of pure functions. It's going to give you the result, the same result every single time you call. So I want to prove to you that this is actually not going to call add until you really need it. How do I prove it? Well, in the case of Java, I often put a print statement. If I put a print statement in Haskell, it kind of stares at me and says, oh, really? You're trying to do this? So I can't do this. I never thought I would use a debugger to prove a point. I feel a little ashamed, so pardon me for doing that. So in this case, I'm going to go ahead and say over here, just bring up the GHCI. And this is, if I know how to type, GHCI. So this is the REPL that I'm going to use for Haskell. And I'm going to say load here the sample.hs, and I'm going to just load this file here. Then I'm going to say break. I'm going to put a breakpoint on line number 1, character number 16. So I'm going to say 1 and 16. Well, now that I put a breakpoint, I'm going to call the main function. Well, as you would see here, it is waiting for me on line number 1 at character 11 and 15. It says, I'm going to wait for this. And OK, thank you for waiting. Continue. And sure, it gave the result of 4. I didn't really prove a whole lot right now, did I? Well, let's come back to this. But I'm going to go back to this code and say, when you call evaluate value equals, I'm going to return a 42. When I run the code, notice the result is 42. But Haskell is very smart. Haskell says, what do you want to do? You say Haskell call add. It says why? Because I want to pass the result to evaluate. Why? Because I want to print it. Okay, let's just print the result of evaluate. It comes in, it runs evaluate, evaluate returns 42. Notice you never cared about value. And Haskell says, gosh, why do I waste time doing stuff that has no meaning? I don't have to really waste my time. Let's be lazy. But laziness becomes from purity. So I'm going to show to you that add was never called. But how do I prove that add was never called? Well, that actually turns out to be really easy after all, because if I go back here and run the GHCI again, go back and put the breakpoint one more time on that line, but this time I call the main method, and in this case, of course, oh, sorry, I messed up here. Let me try this again. So in this case, of course, I'm going to go back, try again. So let's go ahead and say load the file again. So I'm going to load the file. Let's load the sample.hs. Got it. Let's put a breakpoint on line 116. I'm going to call the main function, and notice it never ever stopped on the add function. Well, that's really optimizations that can come through when a language begins to know that you are honoring purity of functions. And this goes a long way. So purity is really the reason I want to really keep things pure and follow these things is because of greater efficiency I get out of it. And that is really the motivating factor for me to really go towards that. Well, that brings up the question then, if functional purity is so important, how in the world can we make those things happen? You know, if I'm programming in Java, you have to work extra hard to make these things work because the language may not be there to safeguard you all the time. You have to have fairly good code reviews. You have to have other tools that check for these things. You may have to do a little bit more work in terms of determining these things. So how do we go about doing this? Well, one of the things I want you to think about is when you write functions, as much as you can, make those functions pure. So this is something you and I can actually do. One way actually we can help doing it is to keep the functions relatively short. Some people have the tendency to write very long functions, long methods. Long methods are evil in several ways. And long methods are really hard to prove what nefarious things they are doing under the hood. So you definitely want to keep methods really short so it's easy to examine them and show that. We can also use tools that can verify for purity as well. But when it comes to purity of functions, we have to really enforce purity. And the reason this is so critical, like I mentioned, is because you cannot get better performance without having the purity of functions. So this is why it becomes absolutely critical. But from that point of view, practical-wise, how is it practical to achieve this? Well, the very first thing is when you write methods, make sure those methods that you are writing are, as much as possible, are pure. I came into work one fine morning, and a buddy of mine said, hey, the code worked really well sequentially, but took a lot of time to run. I made it parallel. I don't even have to tell you what the result was, what the speed was. The result is wrong. And yeah, when the result is wrong, it doesn't matter how fast you got the wrong result, isn't it? So I immediately said, you know what, I haven't looked at the code yet, but I can tell you what's happening. You have a variable somewhere, and it's a field in your class. You're calling a method, and the method is mutating that field. And he stares at me and says, so that's it, huh, your wisdom? It's like, yep, that's it. Now the fun is to go find that out. And we started just looking through the code, and sure enough, 30 minutes later, we find exactly that one little variable being mutated in this one function. It took us about an hour to refactor the code. We run it, we get parallel results much faster, of course, and correct. And mutability really makes it hard to make it parallel as well. So lazy evaluation and parallel requires purity of functions. Well, if that is the case, how could we really achieve this practically in a program? So when it comes to designing an application, I try to use the slogan of a circle of purity with the ring of impurity around it. So what I mean by that is, I'm going to take a circle, and I'm going to say everything in the circle is going to be pure. So I'll build a library of functions, and these library of functions will all guarantee purity for me. And when I'm in this library of functions within the circle, that circle of purity, I will not mutate any variable. I will not mutate any global state. I will not mutate any value given to me. I'm not going to touch on and change the state. I take an input and return an output. That's what I'm going to do. And around the circle of purity, I'll build a very thin ring of impurity. And this thin ring of impurity is where I would read from a database if I want to. I'll do logging. I might do work like, for example, talking to a web service. So a lot of things I can do in the ring of impurity, but the minute I grab the data that I want to work with, from moving forward, once I enter the circle of purity, I will not mutate anything. And I will wait until I exit the circle of purity, and then once I get out of the circle of purity, I can start mutating things again. Because practically, the language like Java does not have this concept of, hey, we're going to really enforce immutability for you. We have to build that around with the limitations that we are going to have in languages like this. So having that model of purity versus impurity, where a circle of purity is where I'm not going to really cause anything impure. When it comes to this purity as well, we have to be careful not only to not mutate variables, but not also to depend on variables that would otherwise be mutable. So that's one thing we can do. In terms of this, however, there's one major concern we all run into as programmers, and that is, if I'm going to do immutability, one way I can do immutability is to copy objects. Well, wait a minute, if I'm going to copy objects, isn't that going to be silly, because we're going to end up with a large number of objects, and that will be not very good in performance at all. So how do we really do with it? Well, this is where we can enjoy from some, what I would like to call as functional data structures. For example, if you really think about list, if you will, the list in languages like Clojure and Scala, the lists are completely immutable. So you cannot modify a list once you create it. So immutable. But when you look at a list, these lists all efficiently provide certain operations where you can add elements to the head. Well, it's not mutable, but what does it mean to add? Well, when you go to a list and you add, here's an example of a Scala code. If you have a list, let's say, of 1, 2, and 3, let's call it as val list is equal to, now you can simply say 0, and then you can put a list into it, and this will be, let's say, list 2 that you get out of this. Well, list 1 is immutable. List 2 is a copy that you get from this given list, and as a result, what did they actually do? Here's a very interesting way to think about how this works. Imagine that the list of people on the front row, imagine that list is immutable. I cannot change that list. Well, I can walk up to the front of the list and declare myself as the first person in the list. With all respect, they cannot do anything about it. And so because the list is immutable, I can declare as myself as the first person in the list. And if you ask the gentleman over there, how many people are on your list, he's probably going to say, I have 5 people in my list. But if you ask me, I'll say I have 6 people in my list, because I'm generously going to share the list that's there. And that's exactly what these languages do. They share existing data because the data is immutable. They can do that very effectively. But of course, you're adding to the head and potentially removing from the head to create another list. Well, if I'm always adding and removing to the head, what kind of data structure is that? Well, that's obviously a stack. So a lot of stack-based algorithms fit really nicely into this. And similarly, what you can actually do is use data structures like trice. A gentleman named Phil Bagwell created this, and a trice is a data structure with a very large branching factor. And with the trice, essentially these are called persistent data structures, and it's called persistent because they are immutable. You're not going to change it. Trice itself was not immutable, but Rich implemented in Clojure and suggested that we can actually make use of it. But because of a very heavy branching factor, the cost of making changes or creating a copy, if you will, is extremely small. Ritchie calls this as effectively constant or practically constant. Well, it's practically constant because it's an order of, let's say, a log n, where the order of log n, but the log of n in this case is, n is not the number of elements, n is the number of levels, if you will. So in this case, of course, if you have 4 levels, because the branching factor is really huge, a branching factor is when you can have many number of children. Trice usually have 32 or more children. Within a 4 level, you can literally pack more than 1 million elements. And to make a copy of that particular million elements collection, you are going to spend an order of log 4, which is practically a constant. I ran some examples with this. I took the vector, which is in Scala, which is a trice implementation, ran it from within Java, and I found out for 100,000 elements, the cost of creating a new one where I changed something right in the middle was something like 33 nanoseconds. And it's been a few years since I ran this actually, but it can be really, really fast as well. So we can start using some of these ideas, but if you really have to poke the data eventually, that's where the circle of purity versus circle of impurity, the circle of purity versus the ring of impurity can come in really effectively. But there's one other issue that we have to deal with. We have to think in functional style. For this, my recommendation is to think declaratively first, and then you are saying, well, now that I know how to express the problem in words, I'm going to try to write functions for it. The JDK has a slew of methods that can help us with this. There are so many methods in the JDK that we can use to do these kinds of transformations. You can take a collection from memory, you can take a file's content, and you can start looping through them in a functional style. So there's a lot of different things you can do with functional style of programming. And as you start writing code itself, to ask the question, how do I express this in functional style? But last thing I want to cover is one very sticky point, and that is exceptions. And I'm sure many of us have felt that pain, right? So when you go to a stream, for example, if you go to a stream, let's say we have a stream with a collection of numbers, and in this case, I want to perform a stream operation. So what am I going to do? Numbers.stream, and I'm going to perform a map operation, given an element, transform the element, let's say, and then I'm going to say, let's say for each, and then I'm going to simply print out that value that's been given to me. So given the element, print it out. But what is the transform method really going to do for me? Well, in the case of a transform method, what if transform was going to give me an exception? Well, notice in this case, let's start with baby steps. A public static, let's say int transform, takes a number, and all it's going to do, let's say, is simply return the number right now. So here is return number. Imagine this is a computation that's going to take some effort. We don't have to worry about it right now. But what if I do something like this? What if I end up doing if number, let's say, is equal to, let's say 7, then I'm going to say throw and new exception, and I'm going to throw some kind of an odd exception. So let's say, oops, something went wrong, just like we get exceptions in our systems, right? And I'm going to say that it went wrong. Well, what's going to happen at this point? This could be a very specific checked exception, whatever name you want to provide for it. At this point, the Java compiler gives you an error. And it says, hey, you cannot throw an exception from this code because on line number 5, you have to say you are throwing an exception. This is only going to get worse as we go through. Now you say throws exception. Now what's going to happen? Java now complains on line number 14. It turns out a lot of these methods don't deal with checked exceptions at all. Why is that? Well, the functional interface simply does not have the functional interface, predicate, consumer, supplier. None of them deal with checked exceptions. On one hand, you could say, gosh, they didn't deal with checked exceptions. But there is actually a really good reason why they didn't provide checked exception. Because doing it is actually not part of a solution. It's part of a bigger problem. So what do we do about this? Let's think about this for a second. If we were going to step back to this and say, OK, I want to really handle this, what do I do? Some people will suggest to you a very dangerous solution, in my opinion. And that is to come in here and take the exception that really happened. Potentially, you're not the one throwing this exception. Maybe this exception is coming from a lower level. When you're calling that other method, that's blowing up with a checked exception. What do? Well, so you probably took this number and you did some other work, right? You called another function calculate over here, and the calculate function, maybe you pass the number over it, and that blew with that exception. So they may suggest to you something like this. They may say, oh, here's an idea. Put a try and a catch around it, and then grab that exception, whatever that exception is, and then, of course, then do a wrapper on it. New runtime exception, and they would even give you convenience methods to do this, and then wrap it. There is a very easy way to describe this. This is called a bad idea. Well, why is this a bad idea? Well, the reason is we didn't really solve the problem. We just quieted the compiler. If you really think about it, that's what we did, right? We went to the compiler and said, shh, be quiet now. And the compiler was like, OK, I'm happy. I won't complain. The problem didn't go away. The compiler just quieted out. This is a disaster. What is the reason why this is a disaster? Well, think about where we are right now. We are in a function pipeline. Now, in the function pipeline, you might have filter over here. You might have more filters right here. And you might have other operations, like, for example, let's say a few other map operations. Who knows how long this function pipeline is going to do? Well, this is a pipeline you are in right now. And when you visualize the pipeline, look at this as a stream of data flowing through from one stage to another stage to another stage. Now, in this pipeline, if one of the things blow up, what do you really do? So the problem with exception handling is exception handling disrupts your call stack. I'm going to go out on a limb and say exception handling and functional style of programming are not orthogonal. They are completely disconnected. It makes no sense to mix them together in that context. Why is this a problem? Let me give you a very stupid example of this. Imagine you are driving on the freeway, and you are about 2 miles away from your exit, and you have a flat tire. What's the worst thing I can tell you? I'm going to tell you, you had a flat tire, now drive in reverse. Go back to where you came from. No, dude, get out safely and pull to the exit, right? So in other words, you always face downstream you never go upstream. And you don't try to jump out of the freeway. That's not safe also. So think of this as a stream. When you're flowing through the stream, you don't exit from the stream abnormally. You still have to exit the stream in the bottom. So when you have a stream where you go upstream to downstream, how do you deal with it? Well, the question is, how do you deal with this in Java? Let me say, I am really a fan of streams. I truly love streams. I am going to tell you that I enjoy streams, I love it, I use it all the time. But that doesn't mean it's perfect. So ask the question, how do streams handle exceptions? They handle exceptions with two beautiful words. They're called good luck. So essentially, there's no answer really. Other languages provide other solutions, but Java quietly said, deal with it. So there's no really good answer how to deal with it. So how do you really deal with exceptions if you're going to deal with it? Well, you can go the hard way and you can deal with it. One of them really is, so this is the difference between the functional mindset versus the imperative mindset. So Java 8 streams really doesn't give you a good answer. One thing you could potentially do here is, you could take on the data. Well, essentially what you really want to do is you want to treat exception or error, let's put it as error, you want to treat error as another form of data. That's what you really want to do. It is just another form of data. And things do go wrong, things do go mess up, and it's okay. You don't want to be smacked on the head when something goes wrong, just deal with it in a very civil way. So what are we going to do in this case? Well, okay, I'm flowing through this processing the data, but something went wrong here, so I'm going to go push that down as an error so you can deal with it downstream. So in other words, but how do you really do this in Java? Sadly, there's no real easy way to do it in the Streams API. Because if I take this in the Streams API, well, I have to now create a structure where I have a data and I have an error and I want to push them down, and Java doesn't quite give us anything like that. There are other languages that provide constructs that deal with these kinds of tuples of data and errors, but Java doesn't have one. So we could maybe look for solutions elsewhere. And such place where we can look for solution is in JavaScript promises. This is exactly what your completable futures in Java do as well, because after all, completable future in Java is nothing but promises in a sense. So what do completable futures and promises do? Well, completable futures and promises say, well, when you have data, we'll flow the data through. In other words, the promises and completable futures, I like to say that they have two channels. And the two channels they have is a data channel, and then they also have what is called an error channel. That's the way I view this. So in other words, this pipeline right off the bat has two channels to work with. You have a data channel and you have an error channel. Or you can say it is a right channel and a left channel. Well, as things go really well, you are just transforming through the data channel or the right channel. When things really go bad, you go to the error channel and you deal with it. So by structure, both completable futures and promises are built with these two types of channels. This is more elegant, in my opinion, as a really better way to handle it, because it promotes that model of let's deal with things downstream. So you give an opportunity for transforming data, but you also give an opportunity for transforming errors as well. One of the ways in which this works is, if things are going well, you keep marching on the right side. If things are not going well, you come to the left side, and you're dealing with an exception. But if you're able to handle the error, you can go back to the right side, and so you can really recover from errors as well, and that gives you a really nice way to handle it. But that, unfortunately, doesn't answer our questions, because a promise literally is still a 0 or 1 piece of data. Or a completable future is a 0 or 1 piece of data. So through a completable future, you may have one data going through, or none goes through. But in a stream, you have n pieces of data that go through. So if you're going to have n pieces of data that go through, you cannot obviously rely on promises to do it. What could we do? This is where the observable ideas begin to take a bit of a root. So observables are flows, depending on what you're using. Observables or flows really are kind of like promises, except that there could be 0 to many pieces of data. So one of the things I really like about observables is they do have a data channel. So just like what we had in the other case, they have a data channel. They also, in addition, have the error channel as well. But in addition to it, they also have a third channel, which is our completed channel. So the completed channel is through which you send a message saying, I don't have any more data. so you can do your cleanup operations. But more important, you have this, again, the data channel and error channel. Through the promises and completable futures, at most one data or one error go through. Through the observables, on the other hand, any number of data may go through. And of course, if something were to go wrong, your error channel will carry the error. So you treat error as data, just another form of data. And so relying on some of these structures gives the opportunity for us to deal with errors downstream rather than trying to disrupt the call chain by throwing exceptions. So this is one of the things I would sincerely rethink when I start programming in functional style, is rethink about my strategy on how I handle with exceptions, because fundamentally throwing exceptions is really doesn't make any sense in the world of functional style of programming. You really want to deal with error as if it's just another form of data, and you want to just push it downstream and handle it. So this is one of the places where I normally start with streams on my projects. I enjoy streams and I use it, but when my project becomes a little bit more complex and we have to deal with a fairly complex amount of exceptions and errors, that's when I consider really looking at something like a observable or flowable, because there is a really better answer in terms of how we can continue using the flow of data, a stream of data, but the data can flow through downstream and we can handle it. And so that is a rethinking of how we want to handle the exceptions. So to summarize what we talked about, when it comes to functional style of programming, sure, languages like Java give us the ability to write lambdas. They give us the ability to write streams, but that's when the real fun starts. Because we can't just walk in and start doing functional programming in language like Java, because there are other constraints, other things we have to be really, really careful about. And unfortunately, keep in mind, as much as I love what Java is doing, as much as the power it gives you, it's a language that will not protect you all the way through when you're dealing with variables and mutability. So you have to take the personal responsibility to make sure you're honoring immutability where it makes sense. You have to control those things, and you have to also take a stab at dealing with things like exception as well in designing these systems. And the circle of purity and the ring of impurity may something help you as well. Hope that was useful. Thank you.